Hello everyone and welcome back to the GAN program again. So the next generation sustainable alternative proteins for food, fundamentals and technological applications. And in the last session we discussed about how can we modify proteins to improve or to get the desired techno-functional properties. We discussed about physical, chemical, biological and so on. And now we are going to little bit slightly different topic, I would say. That's lecture number 13, scaling up production from lab to commercial scale. Okay. I must tell one important thing here is that we are producing alternative proteins for the consumers, right? Especially human beings. I mentioned to you that the population of the globe is increasing and we are going to be about 9 or 10 billion, something like that by 2050. So we need to produce several fold higher food that we are producing today. I have already covered that in my very first lecture, right? We need to produce more food means we need to produce more protein. We also discussed a lot about quantity versus quality, right? Quality is very important. Essential amino acids are important. Digestibility is important. But quantity is also important because we need to feed more and more people. So that means that we need to produce more alternative proteins and we need to extract more alternative proteins. And sometimes we may have to purify alternative proteins to get the desired benefit, right? When we talk about human being population around, let's say 9 billion, if you really want to have a transition from animal-based to plant-based or alternatives, then we need to produce them in a large quantity and we need to purify them also in the large quantity. Large means really large I'm talking about, okay? Now I'm going to talk a little bit about different purification technologies and why we need to purify them. I must also admit one thing that I'm going to take this session, this particular lecture as a freestyle lecture. That means I don't show you a lot of slides now. It's simply because I could not find really nice research articles, especially in the alternative protein area, how they are using large scale purification technologies. I could not find anything, but there's a lot of thing has been done in the milk based area, how they are purifying dairy proteins. In principle, they same or similar technology being applied to alternative protein world, but I don't have a strong evidence to show some good slides for you. I'll take it as a freestyle and I'm going to talk a little bit about why we have to purify, what we are purifying, and how we can purify. Is it clear? The first question is why we need to purify proteins. What do you think about? What do you mean by purification of proteins? Because we talk about many different words. We talked about extraction of proteins. We talked about fractionation of proteins. Now I'm talking about purification of proteins. Are they similar or somewhat similar? Any answer? What do you mean by purification of protein? You have a mic, you should talk now. What do you mean by purification of proteins? Yeah.
Purification, we need to remove these anti-nutrients or other impurities.
Exactly. So we know that anti-nutrients and impurities are the big problems because they compromise the digestibility, right? Even they are present in a very small amount, they can compromise many things. For example, we were discussing about the problems with polyphenol. Remember that color we got? Even the polyphenol content is less than 1%, the protein becomes super colored. And we don't want that color. So we need to further purify proteins. So any other reason we have to purify proteins? All right, I'll give one example now, okay? Why do we have to purify proteins? Rapeseed is a seed. It's an oil-containing seed, right? And after getting oil out of the rapeseed, we get a press cake. This is called cake. Okay, we call it as press cake. And the protein content in this press cake can be, let's say, about 35%, right? And then I use different extraction technology. We discussed about a lot of extraction technology, right? Imagine I used ultrasound or whatever, extraction technology. Or imagine I tried to do air classification after removing complete or something. I did something, right? Now I can get two kinds of main fractions, what we call rapeseed protein concentrate and rapeseed protein isolates. By doing different kind of extraction, I can get these two things, right? And usually you have heard about soy protein concentrate, pea protein concentrate and isolate. And I already mentioned to you guys what do you mean by isolate and concentrate. In general, we believe that the protein content is above 90%, we call it as isolate. There is no strict rule for this one. If it is above 70%, we call it as concentrate. Otherwise, we have flour. For example, pea flour, other flours, they have around 40% ish protein content, right? Now, I'll go back to another point that we have been discussing. Plant proteins are never alone. Even if I say 90% purity of rapeseed protein isolate, it's not a single rapeseed protein that is present in this 90%, right? It's not an individual protein, it's a mixture of different proteins, right? I have gotten it 95% pure, but it's not the 95% pure of individual protein. Does it make sense? Rapeseed contains two types of protein, let's say nepin and cruciferin. Okay, it contains two types of protein, nepin and cruciferin, right? We discussed about nepin has a melting point or denaturation temperature about 100 degrees Celsius, and cruciferin has around 80 degrees Celsius. Let's take that into consideration. Now, if I want to use this rapeseed protein isolate in food products, since they have a difference in their melting behavior or the denaturation temperature, I might get different properties in the food samples, right? Because they are dissimilar. One is an albumin protein, other one is a globulin protein. For example, cruciferin is a globulin, nepin is an albumin. Now we have a mixture of albumins and globulins together. They have dissimilar properties. Perhaps I might get a techno-functional property that is something different than what I was anticipating. Make sense? Now, since they have different properties, now I will start using purification technologies, right? Somehow I can take a nepin fraction out, and somehow I'll take a cruciferin fractions out. This is different than extraction. Can you see? We started with extracting, we get a protein isolate, but the isolate is not necessarily an individual protein. It's a group of so many proteins, and if they're having a different properties, you might compromise functional properties. You might have a good properties, but sometimes we need a different kind of functional properties. Then we need to sub-purify the rapeseed protein isolate, right? And please note that when I say nepin, again, it's not a single nepin. It has its own nepin classes, nepin 1, nepin 2, and so on. Cruciferin also has its own isoforms, so and so. So you can further purify them if you want. Then you get another fractions here, right? Right? And these will have a different properties, perhaps. And that means we started with the crude sample, we extracted something, and then we thought we purified, we got something. No, it's not the end of the story. You're again purifying to get a different things. And that's the concept of purification. Does that make sense? Why we need to purify and how we are purifying today? Is it clear? To get individual, I don't say maybe now I have maybe 90% nepin. This 90% nepin is not equivalent to this 90% rapeseed protein isolate. Do you agree? And here I'm getting like 99% cruciferin after purification. Example, I'm just giving a fake example. This 99% cruciferin has a different functional property than this 90% rapeseed protein isolate. So, and that's the reason why sometimes purification becomes super important to get an individual protein out for a dedicated functional property or dedicated food applications, right? And one thing I must tell you that every purification step you introduce in a process, you lose a protein. A fraction of protein is continuously lost. Often, purity and yield are inversely proportional, right? If you want high yield, you have to compromise with the purity. If you want high purity, you need to compromise with the yield. They are inversely proportional, and often, I don't say every time, but often they are, because every single processing step you're introducing, you lose some part of what you're trying to purify. That's the problem. Process efficiency is never 100%. Okay, of course, we have to optimize it. That's what the whole research in the protein purification world. Am I clear? Why are we purifying and what is the bottleneck here? And plus, every time you purify, you need to spend time and you need to spend money. So when you increase the purity, the cost of the sample, the product can also increase dramatically. Make sense? When you increase the purity, you might get a good techno-functional property, you might not get us as well. However, every step you're introducing, you lose protein or also product is becoming more and more expensive. That has to be one thing we have to taken into account when you say purity. Clear? Any question about why we are purifying? Is it clear, right? Now, we will talk a little bit about how we are purifying today, right? Now I have a rape seed. This is seed, right? Right? My end product, I want nepin, okay? And I want cruciferin. This is my expectation, okay? I would like to have 100% nepin and 100% cruciferin. That's my expectation, right? Now, you should explain me how we can purify these two individual sets of proteins from seed. What would be the steps? I have taught you a lot about extraction already. So many things I have taught. What will be my first step? Right? The first step he is telling that you go for dehulling. Dehulling. Now somebody has to explain me what actually you remove by dehulling. The outer seed coat, and that contains tannins, polyphenols, and all these unwanted things we don't want to eat. Usually seed coat is not so good to eat. They're bitter, though we just want to discard them. Right? How do we do dehulling? Mechanical processes are there. You are chemical engineers or mechanical engineers, you know better than me. So dehulling, there are machines to do the dehulling, let's say. After dehulling, what will we do? Defatting or de-oiling, right? Defatting or de-oiling. Yeah, exactly. They missed one step. We can't do the de-oiling directly on the whole seed. What will you do? Milling. That's why I need help, okay? We need to milling. What do you got to get after milling? What is the product? You get fine powder, okay? Once you have the fine powder, what will be the next step? Defatting, right? The next step is defatting. Can somebody explain how it's being defatted today? Yes, you can use hexane. That's what industrially being used. It's allowed as long as you remove all the hexane from the sample in the oil press. Anything else? Cold press or hot press. We use both cold pressing or hot pressing. It's basically pressing on the rescue. Okay, oil is removed. And what do we get here at the end of the day? Oil and cake you will get. Oil and cake we will get. It's not that cake, okay, it's rapeseed cake. Oil we don't want for now. That is a business of oil industry, and they will take it and they will sell it, they will make money. That's not my problem. We are protein guys now, okay? Now we have the cake. Oil is actually ready to use, but cake is not ready to use. It's only to ready to use for animals. We are animals, but we can't eat cake. This cake. Make sense? Okay. Now defatting finished and I got cake. What do I do next? Extraction. Now I'll go with extraction. Next step is extraction of cake. Okay? Tell me about some extraction. What extraction will you use? Okay, the most commonly used is alkali extraction. I have told you. So I take the press cake. Now it's actually pressed. So it looks like a cake. I don't want to add alkali solution directly to that one. What I will do? I will again mill it, right? I will again homogenize it. So milling or homogenization. Okay, next what will I do? I'll add alkali, right? I will add, let's say, a sodium hydroxide solution containing pH 9, or I'll first add water and adjust the pH, whatever I'll do. So I'll add alkali extraction. Okay, basically I have a big jar containing rapeseed press cake and added with sodium hydroxide. Right. Next, what will I do? Centrifugation or fractionation. The most common, the easiest thing is to do centrifugation, but large scale centrifugation is also expensive. Right? People use muslin cloth or cheese cloth, many things that people use to reduce the cost, right? Let's take it as a centrifugation because you need to separate the two fractions now. I just write it as centrifugation. Centrifugation. Okay? What do I get? So I get two fractions from the centrifugation. I'll come on the left hand side, you can see, right? Okay. You get supernatant and pellet. Supernatant and I get pellet. Right. What will be there in the supernatant? So I will have protein, P for protein. I will have polyphenols, PP for polyphenols. What else? What's that? Carbohydrates. I will have some carbohydrates also here, right? Then anti-nutrient factors, A and Fs. Then what else? What's that? Sodium. I might have a lot of salt. It's coming from sodium hydroxide, and also the seeds also has salt. In the sense they have minerals, like they have calcium, magnesium, and everything. So I will have minerals. Shall I write minerals? All right. What do we have it in the pellet? Mainly insoluble fibers, right? Because they are not soluble in sodium hydroxide, let's say, they're insoluble fibers. That's the main composition. Anything else will be there? Still, there will be some proteins will be there. Do you agree? But a minor content. Only the alkali soluble fraction will come to supernatant. Please note that we are also already losing some protein. First step, we already lost some proteins, a lot basically, right? We don't care about pellet because although some protein is present, it's very dirty. You will throw it or use it for fiber preparation, some other application, right? There's a lot you have to discard also here. It's not a very circular economy bioprocessing. We can do it, but that's another story. Okay, now supernatant has a lot of protein. What will you do? Isoelectric precipitation. So I will do isoelectric precipitation. What will I add? I will add HCl to adjust the pH to Pi. How many fractions I'll get? So I will get a solution here. It looks like this. I will have supernatant and pellet, right? I will have supernatant and pellet. Okay, what do we have in the supernatant? Again, some proteins only, right? Mainly albumins. Okay, we will have proteins. It also globulins will also come. So we have proteins mainly. Do we have some anti-nutrients here? Yes. Do we have some minerals and metals and everything here? Yes. Do we have polyphenols here? Yes, because they are all soluble, right? So we still have a lot of thing accumulated. Now the pellet, what do we have? Small amount carbohydrates you removed a lot here, but still some carbohydrates are left here, right? What do we have left? Still you have a lot of proteins here because those are the proteins, majorly globulins, they are precipitated, okay? Globulins are precipitated, so you will have protein mainly globulins simply because you remember that our PI diagram, all the globulins precipitates at 4 to 5. It's also true for this one. Now, which one is the globulin in rapeseed? Cruciferin. So basically, you will have more cruciferin here. Will you have a nepin here? You might have, but it's very unlikely to have nepin. Why? Because nepin has a long solubility. It doesn't precipitate. What about this one? Which type of protein you will have? Majorly nepin you will have. Okay. And small amount of cruciferin might be also present because some fraction is soluble. It's not precipitate everything. So you have still cruciferin. The major is nepin, less is cruciferin. Here major is cruciferin. So now can you see how you nicely separated two proteins already? You're becoming more and more clever now. Is it the end of the story? Still we have to do a lot, right? Okay, now I need more of proteins now. I have two possibilities. Either I can take supernatant or I can take pellet. Of course, in between there is a centrifugation is there. I did not write. So I have supernatant, I will have pellet. In reality, we will take both of them, but we will process them separately. Okay. Now let's go with the pellet because pellet usually have high amount of protein. Is it okay? You can also work with supernatant, but I'll go with the pellet. Pellet has a lot amount of proteins. What will you do? Okay, so she's telling that she wants to get rid of many things. For example, the pellet will also have small amount of carbohydrates, but small amount of anti-nutrition factor compared to this fraction. Do you agree? Because anti-nutrition factor could be more soluble, so they try to go to supernatant. Right? Polyphenols are more soluble, so they try to go to supernatant. Pellet will have them, but in a small quantity compared to supernatant. That's the reason why I'm going with pellet now. You are welcome to take supernatant to make your life a little bit difficult, but I'll go with pellet to bring with. Now, it also has a small amount of polyphenol, minerals, and everything will be there because they actually bind to the protein. So, when protein precipitates, they will also precipitate. That's the problem, right? So, now we have pellet, and she's telling you will go for membrane filtration or dialysis. Dialysis. So, she will go for membrane filtration. We call it as membrane filtration. What do you get? No. Okay, when you do, I'll get back to that one. When you do membrane filtration, we'll get two things, retentate and a permeate, right? This is a membrane, right? And you add your protein solution to this one. You will get permeate and retentate. The membrane is basically a molecular cutoff, just you cut off based on the particle size, right? That's a membrane. Depending on that, you will cut off. What do you usually get in the permeate? Yes, exactly. So we will have permeate and retentate, and he's telling that in permeate you will have polyphenol, minerals maybe, and retentate protein. Depending on the molecular weight, the pore size of this membrane, you might get protein. Do you get some proteins here? Exactly, some low kilodalton ones that can pass through the holes, pores can also come here, right? Now, this can be further purified because you still have protein, minerals, and polyphenol. I want to get proteins out of it. What shall I do? What's that? You can do size exclusion chromatography, right? Put it on a column. Then I first get protein or I first get minerals. Size exclusion chromatography. The bigger one comes first. So I'll first get protein fraction, and then I will get fraction number 2. I'll get minerals, polyphenols, or something. Now I am getting kind of a very, very pure protein. Am I clear? The same thing can be done in this direction also with the retentate. Same phenomenon. Am I clear? I get some proteins and I'll get rid of minerals. Look, can you look into this? Can you just take a look into this system, what we are doing now? It's not something new I'm telling. Everybody is doing the same thing. So, how many steps we have to get a purity, let's say 80% or 90% or something like that? How many steps can you can count here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There is 100 different steps we can, because you need to prepare other things also in meanwhile. It's not an easy essay, I write it in a box here. But there's so many processing steps involved to get the protein. Originally, protein was in the seed. Now I have protein in my hand. Okay. In between, I used air classification, drying, and so drying is not done yet. So I still have a liquid fraction here, and then I will dry. Then I'll get the powder. And that powder might have 95% protein. Might have, I have no idea. Make sense? So this is the processing we are using today to get alternative proteins in a very, very pure form. In between, they modify too many things depending on the situation. For example, you don't have to do isoelectric point precipitation. Okay? Where do we do isoelectric point precipitation in this diagram? Here, exactly. Here we are doing isoelectric precipitation. Once you do isoelectric precipitation, you get a pellet and supernatant. What you're telling that then we can do membrane filtration, but you don't have to do there. When you have a supernatant and pellet here, the supernatant this here, this can directly go to membrane filtration. You can do that without any problem, depending on the situation, of course. So they will try to modify depending on the situation of what you want to extract. Now, the take-home message is purification is not an easy task, right? You can ask me one quick question. Why can't you do immediately size exclusion chromatography from the scratch? Can you do a size exclusion chromatography here? No, it becomes super complicated. What we're doing, we're trying to sub-fractionize protein slowly. Every step you remove something in this side or this side, right? Every step you remove something, at the end of the day, you get a fraction rich in protein. It's not 100% protein again. Again, it is a mixture of proteins. Again, you have to do another kind of purification. So it's not a thing that ends, in my opinion. So you can do again purification. You can do again do many things depending on what do you want. Any question here? Looks good. When you go home, you will make this assignment. Just close your eyes. Take the protein you want to work with in the future. Maybe housefly, maybe cockroach, maybe microalgae. I have no idea. Hold it in the hand, not the cockroach. Think about hold it in the hand. And now think about how do I get the protein out of that particular biomass, and try to make this flow chart. It is really fun. It's really a good exercise to do at the end of this particular course, because this actually it covers too many things. Once I have powder, then I know all these problems. Digestibility problem, techno-functionality problem, water holding capacity problem, all this problem you have here once you get the protein. Am I clear? And depending on the purity, where do you get the protein? Depending on that, you will have different techno-functional properties. Now, yes.
Sir, out of curiosity, I'm asking. So, whenever we do it in industry, it is a very huge biomass that is converted
Yes.
to get the protein.
Yes.
So, is there that much big size exclusion chromatography to
Yes.
purify?
Good question. Size exclusion chromatography can be scalable, but the biggest problem is that you can't scale to that level you're expecting. It's
Mm.
because, again, in the normal size exclusion chromatography separates by gravity. So basically, you need to pour, wait, and forever. Of course, you can apply some pressure or something like that. It's not very efficient process. However, the membrane filtration is a very efficient process. You don't have to do size exclusion chromatography here. You can do ultrafiltration.
Yes.
And that is efficient, that is scalable, that is continuous. At the moment, people are using
Ultrafiltration.
ultrafiltration or microfiltration, reverse osmosis, electrodialysis, so many other things, because they are all kind of continuous and scalable.
Thank
That's a good question. I'll come back to that again. So size exclusion chromatography is not necessarily a, it's scalable. I'm telling you, it's not unscalable. It's scalable, but may not be that efficient compared to other processes. Maybe I'm not an expert in pilot scale production. I must admit that one also, but I work with people, so I understand. Okay. Any other question? You'll make this homework, right? Great. Now, she asked the question about size exclusion chromatography, is it scalable or not? Usually, you can work with many things, but we try to use in industry a process that can be made continuous. We don't want to use a batch processing method. We don't want to use something has to be cleaned again and again. We want to have things that is continuous, because continuous saves money and time, right? And now you have a final fraction, imagine, that contains, let's say, protein 1, protein 2, protein 3, P1, P2, and P3. And we also have polyphenol. We also have some anti-nutritional factor. And we also have some minerals left. Okay? Am I clear? Now I have a final fraction. It has protein number 1, protein number 2, protein number 3. It also has some polyphenols. It also has some anti-nutritional factor. It also has some minerals. Now, if you look into the composition of the final fraction I have, they have different molecular weight. Can you see? They have a different molecular weight. What does it mean? Their size is also different, in other words, right? Protein 1 may be bigger than protein 2, protein 3 may be bigger than protein 1. Polyphenols are small compared to protein, right? Polyphenol molecular weight, let's say 300 Dalton. Tannin molecular weight, let's say 1000 Dalton. Protein can be 15,000 Dalton, 300,000 Dalton, so big, right? And then anti-nutritional factor. Sometimes they're big, sometimes they're small, depending on whether it's a trypsin inhibitor or whether it's a lecithin. Depending on that, we have a different size. Minerals, very, very small, tiny, right? Do you agree? Now, what I'm going to tell you is that we have different sizes in the system, right? Big one, relatively small one, the smallest one. And depending on the size, we can use different purification technique, filtration technique, right? I found this one is in a very nice article. Depending on the size, what kind of methods can be used to purify. Am I clear? You can see the size of the particle here. Can you see? And the technology here. Proteins are in nanometer size, right? Very small. If it is aggregates, they become micrometer size. Bacteria is in micrometer size, right? Bacteria is in micrometer size. Microalgae is also micrometer size. Cell wall may be in micrometer size. Fibers may be in micrometer size. You are centimeter size, right? I'm talking about the size relativity. So based on the size, we can separate people and things, right? Now if you want to do microfiltration, basically they have a size you can see over here. Okay. If you want to have a size ultrafiltration, they separate from, let's say, 10 to 20,000 or 10,000 they are telling. Usually it's 1,000 to 200,000 according to the literature. So you can use that one, ultrafiltration. You can use electrodialysis, especially to separate minerals, right? You can use ion exchange chromatography to separate proteins with different charges. If you have a bigger particle, very big particle, you can use centrifugation. That's what we did here, right? Because the density is different, by centrifugation you can separate them. You can't separate soluble proteins by centrifugation unless you centrifuge it in next level. Maximum use 20,000 G, let's say. Can you separate soluble proteins 20,000 G? No. Only insolubles will be precipitated, right? So you can use centrifugation if you have a bigger particle. So we are using all these things to get the final product. For example, if your matrix have bigger particles, first you centrifuge it. Okay, then you get this much. Then you do microfiltration. You remove some of the portions. Then you do ultrafiltration. You remove some of them. Then you do nanofiltration. You remove some of them. Then you do reverse osmosis. You remove the final minerals. So it's basically step by step you're doing to get the final so-called ultra pure proteins using membrane filtration. Often people not use all this combination, they use 2 or 3 to get the best ones. Am I clear? So this is the diagram which clearly shows which kind of filtration you can use to get the particles, right? To membrane filtration operates at 1 to 3.1 to 3 bar. It's a flux, the pressure they need to pump to the membrane. Membrane filtration is nothing but the membrane is here. To make it very simplistic way, sorry, it doesn't look like this one. So this is called feed. Feed is nothing but your sample, right? You feed it. And then there is a membrane. They are semi-permeable, permeable. There are different kind of membranes that are available. Membranes will have a hole or pores, right? Depending on the pore size, we call it as microfiltration, ultrafiltration, nanofiltration, reverse osmosis, and so on thing. So you continuously supply your sample to this one and you collect the fraction. Am I clear? So the one it is coming here, it's called retentate. Retentate. The one here is called permeate. Okay, depending on the type of membrane, so we have membrane ultrafiltration, microfiltration, and so on, right? Now, if you want to get only a microparticle from your protein, which filtration will you use? Microfiltration. Microparticles will be maybe self, maybe protein bodies, maybe big chlorophyll. They're all micro, can be gone. Big particles, right? If you want to separate proteins and something else, then you have to go for ultrafiltration because proteins fall in the ultrafiltration range. If you want to separate minerals, osmosis, reverse osmosis you can use. Of course, I don't think there's an electrodialysis here. Electrodialysis can be used. Am I clear? So depending on the need, you need to use different kind of things. Please note that when you do salt extraction, for example, when you do alkali extraction, you have to remove the salt. You can't do freeze drying because salt will be accumulating. That's not good for the health. So we need to do one sort of filtration. It's very common. This is how the filtration system look like, just to give an idea. So the feed is continuously coming. I don't explain all these things. I'm not a mechanical engineering. And this is the membrane what we have. So here you get the fractions, retentate and permeate. Am I clear? And there is something also called diafiltration. Have you heard about it? Diafiltration. In ultrafiltration, what we do, we have an ultrafiltration membrane. Ultrafiltration membranes are very fine membranes. They have a molecular cutoff of, let's say, 10 to 50 kilodalton. Okay, this is ultrafiltration membranes. Basically, proteins can not pass through depending on their molecular weight cutoff here. And some proteins will come here and some proteins will come here. For example, if I use 10 kilodalton membrane, what will happen? Anything more than 10 will be in the top, retentate. Anything less than 10 will be in the permeate. Minerals will also come in the permeate. Do you agree? Because they are smaller than the proteins. So you have to do again maybe dialysis again of that sample, right? And this is called ultrafiltration. In case of ultrafiltration, they can always combine with diafiltration. That means you can continuously add more and more solvent to the system to clean it again and again and again. Then the process becomes diafiltration. Am I clear? Ultrafiltration is often coupled with diafiltration to clean it further, to purify them further. Now, this is the process. Now, I talked about different steps. I talked about membrane filtration that is scalable today. What are the problems you think with respect to membrane filtration for large-scale protein purification? Fouling of the membrane is one of the biggest challenges the whole membrane world is facing because I say they are tiny pores. We are supplying protein with big different sizes and they can block the pores. They can make a thin layer on the membrane, right? They can adsorb on the surface of the membrane. The membrane will foul, no longer allow solution to pass through. Then you have to apply more and more pressure to remove that one. Then the membrane can rupture, right? Process efficiency can be severely compromised if the membrane is fouled. Fouling of the membrane is a problem. To avoid that, there's a lot of researches going on. They're using ceramic membrane nowadays. They're using membrane that is not reacting it with something else. There's a lot of chemistry, physics, mechanical engineering is going on in this field. It's also a nice field to go do research. Am I clear? Dairy industries is using it a lot. A lot means a lot today, membrane filtration to get whey proteins, for example. Am I clear? I don't go deeper into the membrane filtration. That's not my area of expertise, but this is how we are using. Is it clear? Any other disadvantage? Yeah, cost. Basically, the membranes are expensive. If they're fouling again and again, you have to remove it. If they don't foul, for example, you can reuse them. Continuously, you can reuse them. It's only a capital investment, then no problem. Am I clear? But that's not in reality. Any doubt about membrane filtration? Is it clear? Membrane filtration is nothing but a filtration used based on membrane. Depending on the type of membrane, we have microfiltration, ultrafiltration, nanofiltration, reverse osmosis. Each of them will pass through one type of molecule depending on the size, and that can be exploited to purify proteins from small molecules. Okay, ultrafiltration is often used combined with diafiltration today. Apart from membrane filtration, people also use adsorption chromatography. We have a company in Denmark, I found it is from their website, And they are trying to use kind of, you can find this in the YouTube video. If you go to this website, they have a nice YouTube video how they're using. Instead of using membrane, they use an adsorption stuffs basically. Proteins have affinity for ligands, right? They bind to some kind of, I don't know what they're using here though. They bind to, they bind to this kind of particles here. And when they selectively bind to the particles, you can purify proteins. Okay? Basically, I think I taught you this affinity chromatography earlier, right? You have particle, okay, and you have protein. If this particle likes protein, it will bind, right? The rest everything will go away. Then you would an elution buffer to remove proteins away. Okay, so these kind of technology can also be used for large scale purification of proteins. Am I clear? Often membrane filtration is used, but I found this company, they are also using other kind of technologies to purify. Please note that certain things are very scalable. I would found it from their internet on their website that they say they can manufacture, or this can be scalable to very large scale, something like that. So there are big equipment to purify proteins. For example, to purify dairy proteins, you're talking about the pilot, the plant, it could be like of the whole building size. So it can be made very scalable. All right, that's all about large scale purification. We get an extract, we are not happy. We want to get an ultra pure protein. If you want to get an ultra pure protein, you have to use different technologies. Often used is membrane filtration, and that gives you a highest purity. I don't know about yield. It varies from process to process, protein to protein. And there is no evidence. People are using, I know, but in the internet, I could not find a lot of articles on how alternative proteins are being purified today. There's a lot of article on milk, but alternative protein, there's a less article because some of these technologies are patented and they don't want to tell you what they are doing. So that's a problem. So we don't have scientific research. That concludes my last lecture of today, large scale purification of proteins.